Simplifying Fractions, Part 1. In the last lesson, we went over the different parts of fractions, numerators and denominators, how improper fractions can be converted into mixed numbers, and how to convert mixed numbers into improper fractions. In this lesson and the next, we will learn how to factor numbers so that we can rewrite fractions in what is called their simplest form. So, let's begin. When we multiply two numbers together, with the exception of 1 and 0, we produce a different number. For example, when we multiply 2 times 3, we get 6. When we multiply 5 times 7, we get 35. Likewise, when we multiply 2 times 5 times 11, we get 110. Numbers such as 6, 35, and 110 are called composite numbers. That is, they are composed of other numbers. And the numbers they are composed of are called factors. In these examples, 2 and 3 are the factors of 6, 5 and 7 are the factors of 35, and 2, 5, and 11 are the factors of 110. Can you list the factors of 15? The factors of 15 are 3 and 5, because 3 times 5 equals 15. How about this one? What are the factors of 8? There are actually two answers to this problem. 2 and 4 is one answer, because 2 times 4 equals 8, and 2, 2, and 2 is another answer, because 2 times 2 times 2 equals 8. In the case of 2 times 2 times 2, the factors are given a special name. They are called prime factors. To understand what prime factors are, you first need to understand what a prime number is. A prime number is a number that has two factors, 1 and itself. 2 is a prime number because its only factors are 1 and 2. 3 is a prime number because its only factors are 1 and 3. 5 is a prime number because its only factors are 1 and 5. Is 7 a prime number? To answer this question, ask yourself, what are its factors? 7 only has two factors, 1 and 7. So yes, 7 is also a prime number. The first 10 prime numbers are 2, 3, 5, 7, 11, 13, 17, 19, 23, and 29. Why? Because each of these numbers has only two factors, 1 and itself. Okay, so that's what prime numbers are. What about prime factors? A prime factor is simply a prime number that is being multiplied by another number. In the expression 4 times 2, 2 is a prime factor because 2 is prime and it's being multiplied by another number, in this case, 4. In the expression 5 times 3, both 3 and 5 are prime factors. Now that we know what prime and composite numbers are, let's learn how to identify all the prime factors of a composite number. There are many ways to accomplish this task, but my favorite is to use a factor tree. In a factor tree, each layer contains one set of factors. Here's an example of a factor tree for the number 20. In the first layer, we have 2 and 10, since 2 times 10 equals 20. We keep moving down the tree until the bottom level only contains prime factors. Here's another version of a factor tree for 20. Notice that the top layer lists 4 and 5 as the factors of 20, but we still end up with the same set of factors at the bottom of the tree, 2 2s and a 5. This is because every composite number has just one set of prime factors. The route to get these prime factors may be different, but the destination is always the same. Creating a factor tree for 20 seems easy enough, but what if you were asked to factor the number 129? Where would you begin? Well, there are a lot of tricks you could use to start a factor tree, but I'm only going to show you 3 of them, because the other ones get much too complicated. So complicated, in fact, there's a good chance you'd forget them anyhow. At least, I probably would. Here's the first trick. If a number is even, it has 2 as a factor. For example, 6 is an even number, and its factors are 2 and 3. 2 times 3 equals 6. So, do you think 10 has 2 as a factor? It's an even number, so yes. 2 times 5 equals 10. By the way, we say that even numbers are divisible by 2 because they can be evenly divided by 2. For example, 16 is divisible by 2 because 16 divided by 2 equals 8. 200 is divisible by 2 because 200 divided by 2 equals 100. Now let's move on to the second trick. If the sum of the number's digits is divisible by 3, so is the number. For example, is 3,981 divisible by 3? To answer this question, we could divide 3,981 longhand, or we could add up the number's individual digits and divide by 3. That is, we add 3 plus 9 plus 8 plus 1 to get 21. Now we ask ourselves, can 21 be divided by 3? Yes, it can. 21 divided by 3 equals 7. Strangely enough, this tells us that 3,981 can also be divided by 3. Let's take a minute to prove it. 3 goes into 3 one time with a remainder of 0. 3 goes into 9 3 times with a remainder of 0. 3 goes into 8 2 times with a remainder of 2. So we bring down the 1 and 3 goes into 21 7 times with a remainder of 0. What does this little exercise tell us? It confirms that 3,981 is in fact divisible by 3. And therefore, the first layer of our factor tree could look like this. Of course, we would have to complete our factor tree by factoring 1,327, but let's not worry about that for now. Let's try one more problem to make sure I've explained this clearly. Is 2,361 divisible by 3? Let's add up its digits and find out. 2 plus 3 plus 6 plus 1 equals 12. Is 12 divisible by 3? Sure is. 12 divided by 3 equals 4. Therefore, 2,361 must also be divisible by 3. Let's check to make sure. 3 doesn't go into 2, so we divide 3 into 23 to get 7, with a remainder of 2. We bring down the 6 and divide 3 into 26 to get 8, with a remainder of 2. Finally, we bring down the 1 and divide 3 into 21 to get 7, with a remainder of 0. So yes, 2,361 is divisible by 3, and therefore the first layer of our factor tree could look like this. Okay, last trick. If a number ends in a 0 or a 5, it has 5 as a factor. Let's look at 10, 15, and 20. They all end in a 0 or a 5. Do they all have 5 as a factor? 5 times 2 equals 10. 5 times 3 equals 15. And 5 times 4 equals 20. So yes, they all have 5 as a factor. These examples also provide evidence that the trick works, because all three numbers end in a 0 or 5, and they all have 5 as a factor. Now, armed with our 3 tricks, let's create a factor tree for the number 60. There is no rule that states we need to use the tricks in any special order. So let's begin by checking to see if 60 has 2 as a factor. It's an even number, so it must. We divide 60 by 2 to get 30. We can draw 2 branches off 60 and place a 2 under the first branch and a 30 under the second branch. 2 is a prime number, so we can leave that branch alone. 30 is an even number, so again, we know that it's divisible by 2. 30 divided by 2 equals 15. So we can draw 2 branches off of 30 and label one of them with a 2 and the other with a 15. Again, 2 is a prime number, so we can leave that branch alone. Now, 15 is not even, so let's move on to see if it's divisible by 3. Do its digits add up to a number that is divisible by 3? Well, 1 plus 5 equals 6, and 6 is divisible by 3, so yes, 15 must also be divisible by 3. 15 divided by 3 equals 5. So we can draw two branches off of 15 and label them with a 3 and a 5. Now we see that all the branches are labeled with prime numbers. So we write the prime factors of 60 as 2 times 2 times 3 times 5. Let's do a quick check to make sure we get back to 60 by multiplying our prime factors together. 2 times 2 equals 4, 4 times 3 equals 12, and 12 times 5 equals 60. Perfect, just as we expected. Let's try another problem. Let's list the prime factors of 105. What trick do you think we should use first? Well, 105 ends in a 5, so let's use the trick that says if a number ends in 0 or 5, it has 5 as a factor. So let's divide 105 by 5. 5 doesn't go into 1, so we divide 5 into 10. 5 goes into 10 two times with a remainder of 0. And 5 goes into 5 once with a remainder of 0. So we get 21. We place a 5 and a 21 on the two branches from 105. 5 is prime, so we can leave that branch alone. Let's apply our tricks to 21, even though you probably already know what the factors of 21 are. 21 doesn't end in a 0 or a 5, so 5 isn't a factor. It's not even, therefore 2 isn't a factor. So let's try 3. We add 21's digits, 2 plus 1, to get 3, and 3 is divisible by 3. So this means 21 has 3 as a factor. And of course, 21 divided by 3 equals 7. So we draw two branches coming from 21 and place a 3 on one of them and a 7 on the other. So the prime factors of 105 are 3, 5, and 7. Okay, let's do one more problem, but this time we'll use a number that doesn't fit quite so nicely with all the rules. Let's choose 154. 154 is even, so we know 154 has a factor of 2. 2 doesn't go into 1. 2 goes into 15 7 times with a remainder of 1. We bring down the 4, and 2 goes into 14 7 times with a remainder of 0. So we have 77. Our branches now end in 2 and 77. Is 77 an even number? No, so it doesn't have 2 as a factor. Does 3 go into 77? Let's see. 7 plus 7 equals 14, and 14 isn't divisible by 3. So 3 isn't a factor of 77. Okay, does 77 end in a 0 or a 5? No, so 77 doesn't have 5 as a factor. So now what? We've gone through our 3 tricks. What can we do? Well, 77 could be a prime number, and we'd be finished. But it's a little big to make that assumption, so we'd better check. The way we can determine whether 77 is a prime number or a composite number is by dividing 77 by the first number in our prime number list that we haven't already used. Let's see, we've tried 2, 3, and 5, so let's check to see if 77 can be divided by 7. 7 goes into 7 one time, remainder 0, and 7 goes into 7 again, one time, remainder 0. So 77 divided by 7 equals 11. Now we can place a 7 and an 11 on the branches leading from 77. Since 7 and 11 are both prime, we know the factors of 154 are 2, 7, and 11. I should point out that if 7 didn't go into 77, we'd try the next prime number, 11. If 11 didn't go evenly into the number we were trying to factor, we'd try 13. And we'd keep going down the list until we were convinced the number we were trying to factor was prime. As I mentioned at the beginning of this lesson, there are 2 topics we will be covering in this lesson and the next. 1, factoring composite numbers, and 2, simplifying fractions. We have finished up the first topic, and we'll move on to the second topic in the next lesson. But before calling it a day, how about doing some factoring problems on your own? Good luck!